Hello, everybody. So what we're going to do now is the second half of the exam 2 practice questions. So in the first video, we did 3 or 4 proofs, induction proofs. 1, 2, 3, 4. 4 induction proofs. So we have 1 proof left and also the rest of the exam. So let's go ahead and get right into it. So um, Problem 5 here says complete the following steps to prove that f of 5n is divisible by 5. So if you look at the Fibonacci numbers here, let me just write some out. So like f1 is 1, f2 is 1, f3 is 2, f4 is 3, f5 is 5. So notice that when that's a 5, that's a 5. Right? And so this is every number divisible by 5 is supposed to be have a Fibonacci number that's divisible by 5. So f6 is 8, f7 is 13, f8 is 21, f9 is 34, f10 is 55. So again, notice that the ones that are divisible by 5 here, this one and this one, the index is divisible by 5, 5 and 10, and then the Fibonacci number is also divisible by 5. And so that pattern actually continues forever. So like if you were going to look down here at like f, 35, like what is it? Well, I don't know, but I know it's divisible by 5 because that's what this theorem says. Okay, so that's what we're proving, is that all of these are going to be divisible by 5. Okay, so I mean, there's nothing to it. We just need to get in here and get started. So let's go ahead and do that. So it says like, what is the basis step? So we need the basis step here. So the basis step is always, true for n equals 1, right? This does start at 1. But when n is 1, we're actually looking at f5n, so f5, right? So there's nothing to do here, right? You just say f5 times 1 is, of course, f5, which is 5, and that's divisible by 5. So that's it. f5 is 5, which is divisible by 5. Okay, now for the induction hypothesis, I don't think we need strong induction here. I think we can get away with regular weak induction. So I think for our induction hypothesis, we just want that it's true for n equals k. So I think that's all we want. So what would that mean? We would say assume that f5k is, well, it says it in words, right? So is divisible by 5. But you probably want to have that as like a mathematical statement, like an algebraic statement. So instead of writing it in words like this, you probably want to write it like this. F5k equals like 5, I don't know, m maybe, for some integer n. Right? Just like we use like a number equals 2k when it's even, right? You could use 5m for some integer m to indicate that it's divisible by 5. So we're probably going to use like this form here. Now, then it says, what do we need to show that it's divisible? What do we need to show for the induction step? So we need to show that it's true for the n equals k plus 1 n equals k plus 1 case. So specifically, we need to show that f5 k plus 1, which of course is f5k plus 5, is divisible by 5. That's what we need to show. Okay, so then we're going to go ahead and do it. So what you do here is you're just going to repeatedly use the the formula for the Fibonacci numbers. Basically, we're going to do this a little bit differently than previous induction proofs. We're going to start with this f5k plus 5, and we're just going to keep breaking it apart until everything gets down to f5k, right? And we can do that because if we start with, like, I'll start way over here. If I start with f like 5k plus 5, right? I know that f5k plus 5 is f5k plus 4 plus f5k plus 3, right? Because if you add two consecutive Fibonacci numbers, it creates the next one. So we broke 5k plus 5 into 5k plus 4, 5k plus 3. Well, that's great, but we need to break these apart now. We need to keep breaking them apart until we get down to 5k. So it's actually a little bit kind of tedious here, but we just have to do it. So like the 5k plus 4 is a 5k plus 3 and a 5k plus 2. And the 5k plus 3 is a 5k plus 2 plus a 5k plus 1. So we're getting there. Keep going. Of course, this 5k plus 3 can be broken apart into a 5k plus 2 and a 5k plus 1. This is a 5k plus 2, which would break apart into a 5k plus 1 and a 5k. Hey, we're getting there. We have another 5k plus 2, so that's going to be, we could have done them both at the same time, but we didn't. So I'll have to write it again. A 5k plus 1 and a 5k. And then you have this 5k plus 1, and actually that's good enough. So we're just going to leave that as 5k plus 1. Because we don't want to break that apart any further, because if you break it apart, it'll turn into a 5k and a 5k minus 1. And we don't want a 5k minus 1. We want 5k to be like as low as we go. So we can't make everything a 5k, but we can make everything a 5k or a 5k plus 1. So 5k plus 1, 5k, 5k plus 1, 5k, 5k plus 1. Is this supposed to be 5k plus 1? Yeah, it is actually, right? It's supposed to be a plus 1 there. So we're getting there. The only one we have left to do is this one. So let us do it. It will be a 5k plus 2, so it'll be f 5k plus 1 plus f 5k plus f 5k plus 1 plus f 5k plus 1 plus f 5k plus f 5k plus 1. I should have copy pasted f 5k plus f 5k plus 1. Okay, hopefully I counted those right. But here's what you want to do. So count up the 5k plus 1s. Here's one, here's one, here's one, here's one, here's one. There is 1, 2, 3, 4, 5 of them. So there are 5 f5k plus 1s. Plus, and then if we count the remaining terms, we have a 5k, a 5k, and a 5k. So those are 3 f5ks, right? But then this is where you get to use the induction hypothesis, because by the induction hypothesis up here, f5k is 5n for some integer n. So you can come here and you can say, well, this is equal to 5 f5k plus 1 plus 3, and then replace the f5k with 5n. And now both of these have a 5. So you can factor out the 5 and have f5k plus 1 plus 3m. And so this is clearly showing that this up here, the f5k plus 5, is 5 times an integer. So this is divisible by 5. So that's what we need to do, is get from here to 5 times something. And we showed that it is divisible by 5. Once we've done that, we're done. We just need to make our conclusion. So f5k, actually, we're going back to writing the conclusion so we can use the original variable n. f5n is divisible by 5. For all n equals 1, 2, 3, dot, dot, dot. So that's it. So that's a very common proof when you learn about induction proofs, and it's not that bad. You just have to kind of know what your game plan is. Just keep breaking it apart, and eventually there'll be a 5 everywhere because there's 5 of one thing and the other thing is divisible by 5. Okay, so next question. So on the next question here, we are going to use the merge sort algorithm to sort the following list. So this is pretty straightforward. We just need to write it up. So the way the merge sort works is it is going to repeatedly split this list in half. That's the first part of it. So we split it into the first half, 8, 3. How many things are here? Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when we do this, it's going to be 5 and 5 to start with. So 8, 3, 6, 1, 10. And 5, 2, 7, 9, 4. Okay, split each of those in half. And it doesn't really matter how you do this, but with 5 things, one's going to get 2 and one's going to get 3. And the way that it's coded up, we round down on the first list. So generally, the first list will be the smaller list if you use our algorithm. Right? So split it again. Each one, 8, 3, 6, 1, 10. We got a 5. Don't know why I wrote that like that. We got a 2. We have a 7, 9, and 4. Now, you have to keep splitting the lists until things are down to a list of size 1. So a lot of these are already done, right? A lot of these are already lists of size 1 here, here, here. But this one's not, and this one's not. So we do need another row. So generally what you do is just you only write the ones in that need to go to the further row, like that. Okay? And then once you have that, we need to work backwards. So you can kind of think about like an imaginary line right here, or in this case, an actual line, not an imaginary line. And we're going to go back the other direction. So sometimes they rewrite them here like this. So we can think about the steps going backwards. So when we put these back together, they get put back together. But when they're put back together, if necessary, they're put in order, right? Because technically, this is a sorted list. It's already in order. This is a sorted list already in order. And when you put them together, the result will stay sorted because that's what merge does, is keep them sorted. So you add the 1 and the 10 to the same list, and you'll get 110. Here you add the 9 and the 4 to the list, and it will put them in the right order because that's what merge does. So you put those back in, and at this point, what you need to do essentially is you just carry these all down to the new row. So we got an 8 and a 3, and we bring the 6 down, and we bring the 5 down, we bring 2 down, and we bring the 7 down. And then we can start combining them again. So the 8 and the 3 will become a 3 and an 8. The 6 and the 1 and the 10 will become a 1, 6, 10. The 5 and the 2 will become a 2 and a 5. The 7 and the 4 and the 9 will become a 4, 7, 9, right? Keeps them sorted as you go. Then these two combine. We're going to have a 1, 3, 6, 8, 10. these two combined, we're going to have a 2, 4, 5, 7, 9. And then finally, we combine them into one more sorted list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's done. So that's how you would show the merge sort algorithm working. There is an example in the book and also examples in the notes if you need them. Yeah, so that's it. All right. Now here I say give a recursive algorithm. You can write code if you want here or pseudocode, however you want to do this. I'll probably just write like MATLAB code myself, but you don't have to. So like a recursive algorithm for computing in X is going to be very simple because they say n is a positive integer. So the idea is pretty simple. Like if you're going to do like 3x, right? That's just x plus x plus x, right? Or rather, the idea is if you want to calculate 3x and you only want to use addition, then you can say that 3x is going to be, you take 2x and then you plus x. And then that's going to be it. So what would an algorithm look like? Well, we can just write it. Again, I'm just going to write MATLAB code, although you don't have to. So like I'll say function like y equals, and what are we going to call this? I don't know. Just maybe mult. No, that's a bad name. Mul and multiply by an integer. That's what I'm calling it. I don't know why. And what you have to give it is the n and the x. So n x. Okay. And so basically what you need to do is the basic thing is going to be a formula like this, right? The result is going to be equal to like 3x would be 2x plus x. So we'll have a line like this, but you can't just do this, right? You can't just say like, for example, y equals multiply integer, right? It's a recursive function. You can't just say this. So what's supposed to happen is the number, the n, goes from 3 to 2, right? So we would subtract 1 from the n, and then keep the x the same, and then we would add x, right? So this is, this right here, this line is how you would implement this formula. Now the problem with just having this line here is that there's no kind of base case, right? The way that we wrote it is this would just keep subtracting 1 from the n. There's no bottom. It's never going to stop, right? Like if you tried to do this with a 3 and like a 2, the n would go from 3 to 2, and then from 2 to 1, and then from 1 to 0, and then 0 to -1, etc. So it just never stops. So this needs to be in some kind of if statement here, right? So this would be like if n is greater than 1, probably you would do this, right? And if it's not greater than 1, so that in that case it would be 1, then what would you do? I think probably we would just that, right? And I think that would do it. Yeah, and that makes sense, right? Like if you called this function with, like for example, if you called this function with mul int like 1 and like, I don't know, 7, right? Then of course that's supposed to be computing in x, so 1 times 7, the result should be 7. And what will happen when you do that is It'll check if n is greater than 1. It's not because n is 1. So this gets skipped. It does the else, and then y equals x, which the x was 7. So it would return 7 in this case. But if you put a 2 here, for example, then what would happen is the first time through here, it would check if n is greater than 1. It is. So it would tell you that y is equal to mul int n minus 1. So it would basically do this, y equals mul int 1, 7 plus 7. And when you do the mul int 1 comma 7 plus 7, this is going to return 7, right? We already saw that. And then a 7 plus a 7 would be 14, which is the correct value. So this will work. So this is how you would do it. And again, you don't have to write it in actual running code, but it doesn't hurt to do that. So this is a recursive algorithm for doing this multiplication here. And yeah, that's about all I have to say about it. So next one, give a recursive algorithm for finding the sum of the first n positive integers. So again, what we're going to have is like, if you put in like a 7, right? That's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. But you can think of it as we can take the n minus 1 version of that and then just add this, right? So like, if I call my function like sum, let me get a return variable, y equals like sum n, I don't know what to call it. And you just pass in the n here. Then what you can do is the basic formula would be that the return should be, well, we run the algorithm on n minus 1. That would be to add up like the first 6. But to the first 6, you need to add the current one, which is n. Right? So that's like the basic formula there. Like in order to calculate, I don't know why I wrote 7, but like the first 7 integers, right? You would add up the first 6, which this does it, and then you would add the 7th, which happens here. Now, like before, the problem with this is there's no kind of base case. It doesn't start somewhere. So just like the other one, you only do this if n is greater than 1, right? If n is going to be equal to 1, which it will be because we're starting with positive integers, so n has to be a positive integer. So it'll be 1 or more, and then you'll be counting down. So it will get to 1 eventually. And when it gets to 1, well, you would just add 1. So again, that should work. Because the way it works is if you called this, for example, sum n like 4, for example, what would happen is it would check if n is greater than 1, which it is. And then so it would say that, well, y is sum n minus 1, which is 3, plus 4. But then what is sum n 3? It is sum n 2 plus n, which is 3. But then there was already this 4 here. And then how would you calculate sum n2? Well, sum n2 would be sum n1 plus 2, and we already had the 3 and the 4. And then when you calculate sum n1, well, this would not happen. If n was 1, you'd end up in the else, and then y equals 1. So you would end up with a 1 there. So you would get 1 plus 2 plus 3 plus 4. Right? So that's how you would do it. So pretty straightforward. None of these are that bad. Again, you don't have to write code like I did that runs, but if you do, it will not hurt. If you wrote it in like Java or something, I would not mind. Yeah, so that's it. Let's move on. So this is just writing out terms in the sequence. This is just to see, just to make sure we know how to calculate these. There's nothing super complicated about it. So like you say A1 is 7 because it says so here. And then after A1, you have to use this formula. So if you wanted to calculate A2, you would say A2, well, when you have A in here, when this is an n, this is an n minus 1. So A2 would be the square root of 10 plus 3 times A1. So it would be the square root of 10 plus 3 times 7. So I'm just going to use a calculator and round to 3 decimal places, just like I said. So we have a square root. Find a calculator here. Where's the square root? Square root. So 10 plus 3 times 7. So square root 31, which is 5.568 when you round. So then you're going to take A3, which is the square root of 10 plus 3A2, and you're going to have to put in this 5.568 in for A2. So we have 10 plus 3, 5.568. So you work that out on the calculator. We've got square root 10 plus 3 times 5.568. And I get 5.168. A4 would be 10 plus 3A3, which is square root 10 plus 3, 5.168. Work that out. Square root 10 plus 3 times 5.168. I get 5.050. And finally a 5, which is the last one it says to do. So we barely have room. 10 plus 3A4. So 10 plus 3, 5.050. So we have square root 10 plus 3 times 5.05. And I get 5.015. Okay. So that's it there. We're just calculating numbers. And then it says, we can't show that the sequence converges. That's out of the scope of this class. You do that in a calculus class. But if we assume that it does converge, what does it converge to? Just looking at the numbers, you can probably guess that it's going to 5, right? Like 5.5, 5.1, 5.05, 5.01, right? It does seem to go to 5, but if you wanted to show that it goes to 5, we can do that. Because if you do this, you say, like, if you say assume, like the limit of an is L. Well, if an goes to L, then also an minus 1 goes to L. Because if n is infinity, if n is infinity, then it doesn't matter if you have an or an minus 1. If n is infinity, then this is a infinity and this is a infinity, so they're both going to be equal to the limit, whatever the limit is. So I'm assuming there's a limit there. If I assume that there is a limit L, then you've got this an equals square root 10 plus 3 times an minus 1. You can just say as n goes to infinity, what happens? Well, as n goes to infinity, you get to the limit. So the an here is going to be L, and the an minus 1 is also going to be L. So you get this equation here, and then this equation can be solved. So you just solve this. So how would you solve it? Well, square both sides like that. Put everything on one side of the equal sign. And then factor. So we're looking for numbers that multiply to -10 and add up to -3. So we end up with -5 and +2. So L minus 5, L plus 2. And then that tells you that the limit would have to be L would be 5 or L would be -2. Now it could not possibly be -2 because the way the sequence is defined, right? All of the terms in the sequence come from a square root, and you can't take the square root of a negative number. And when you take the square root of a positive number, you're going to get a positive number. So there's no way that this could possibly be going to -2. So you just throw that out and you just take the L equals 5. So you'd be able to say, so if there's a limit, if there is a limit, it must be 5. Now that doesn't actually prove that there is a limit, but obviously there is because, when we calculate these numbers up here, we see it going to 5 anyway. But technically, we did not prove anywhere that it actually has a limit of 5. We proved if it has a limit, the limit is 5. Slightly different. Okay, so that's how you do that. And we got one more recursively defined sequence. So this is just meant to be a little, I don't know, tedious, just to give you something to do. I don't know. We're calculating A5 through A10 here. A1 through A4 are defined, and then for anything after that, you have a formula to use. So I don't know. It's not that hard. So like A1 is 1, it says. A2 is also done for us, is 1. A3 is done for us, it is -2. A4 is done for us, it is +2. And then at this point, we have to start using this formula here. So to calculate the A5, that's not what I wanted. To calculate the A5, well, be careful looking at the indices, right? So when this is an n, this is n minus 1. That would be like an A4. But this is an minus 3. So you actually have n minus 3. So n minus 3 here would be, if n is 5, 5 minus 3 is 2. Right? So it's actually looking at the indices. Whatever number is here, 5 in this case, this is going to be 1 less, and this is going to be 2 less than this one, or 3 less than the original one. So, just keep that in mind as you're going. And then we just fill in the numbers. So the A5 is A4 plus A2, which is A4 is 2 and A2 is 1. So 3. And then A6 is, again, 1 less, and then 3 less. Or another way to think of it is just like these numbers, 5, 6 are going to count up. These are going to count up 4, 5. These are going to count up 2, 3. Just so you don't make a mistake there. So A5 plus A3, A5 is 3. A3 is -2. So we have 3 minus 2, which is 1. A7, it's going to be A6 plus A4. So A6 is 1. And A4 is 2, so we get another 3. A8 is A7 plus A5. So A7 is 3. A5 is Also 3. So 3 plus 3 is 6. A9 is A8 plus A6. A8 is 6. A6 is 1. So we have 6 plus 1, which is 7. Finally, A10. A10 is going to be A9 plus A7. So A9 is 7 and A7 is 3. So we end up with 10. So we did it, right? That's what we were trying to do. So, that's just making sure we can calculate those numbers correctly. It's not that bad. And I think that's it, right? So that's the end of the practice quiz here, or practice test. Real test will be just like this. Let me know if you have any questions via email, I suppose, over the weekend. Okay, so that's it for now. I will talk to you guys later.